There are many people who take astronomical photographs. You have these very star-like objects. You have stars and that you want sharp, but you also have nebulas that you want to show nicely. And you have all these other things, the pillars of civilization, of the world, and so on. All these things have smooth parts and very pinpointed things. And you want all of that in its full glory. And it's wonderful that Wavelets help show that glory a bit better. My name is Ingrid Daubechies. I'm a mathematician. Although I was trained as a physicist, I shifted towards applied math. I didn't notice. People described me as an applied mathematician, so it was fine with me, as long as I could do what I wanted. I work at Duke University, and I have worked on wavelets and their application. I've been interested in understanding how things work and how to figure things out as long as I can remember. And I learned very quickly that you needed math in order to describe stuff, physics, nature. Well, you need words, of course, and that's how I learned first. But then as soon as you want to figure out things, and I like math for its own sake as well, because figuring out is fun. And so I can't put my finger on when I didn't have a sudden aha moment. Oh, I want to do that because it's been part of what I like doing for as long as I remember. What I like about mathematics is, well, it is something in which you can formulate and then work on problems, on situation, on getting insight, getting understanding of or building things that you couldn't do before. So I see it as a challenge always to, can I do this? Does it work? I know how to do this, or maybe I need to learn some more mathematical tools before I can attack this particular problem. And then I do. And I like working with people. I like collaborating and explaining things to each other so that together we get further than each of us was individually. I find all that in math. When I was younger, there was a stage where I wasn't sure that I would be able to find a job because it was very difficult. It was a period where it was very difficult to get jobs in mathematical or physics research. But I had decided then that what I really liked about my career so far was the creativity aspect of it. And I had decided, well, if I can't get a job in scientific research, then I will still try to find a way in which to be creative otherwise. I mean, there was a period where I was very uncertain, but I was finding my peace with possibly having to change direction. But realizing that this creative problem solving, creative out-of-the-box approaches to challenging situations was what makes me tick. And that I might find that elsewhere was important. I was fortunate in that I did find jobs, a succession of jobs that enabled me to stay in research. And I'm happy with the life I've led. But these creative sparks are really what I find the most interesting and exciting. Actually, it's to the point where when a problem declares itself, my family says, now, don't get into problem solving mode. Not yet. Wait. So, because they know that I will be trying to, and I may come up with off-the-wall solutions, and they first want to try more conventional approaches. So it's a family joke. To be a really impactful researcher, I think a major component is luck. It's also being prepared. I mean, you need to know a lot of things, to know a lot of approaches. You need to have internalized ways of looking at problems from different angles. You need to have at your fingertips several techniques but there's also luck plays a role, because being the right person at the right moment for the right problem I know many people who I think are as creative and as smart and as driven as I am, and who have had maybe less of an impact, because I've been very lucky in that I was confronted with really interesting problems at a moment that the solution to them, which I found had the possibility of having an impact. So that plays a role. And I think it's important for people who are in that position to realize that did play a role. We're part of a big community of wonderful, creative people who are very collaborative and who are working together. I really see us as a big interwoven network that produces results. And some people play a bigger role than others in some of the end branches that then are visible from the outside. But without the network, I don't think it would be possible at all. So I think luck and the community is important. The Wavelet building blocks are things for which we have a fast algorithm for decomposing things into these building blocks. But each of the building blocks, although I can render it very precisely, it doesn't have an analytic formula. It's defined by the algorithm. And it's also, because we have a fast algorithm, you can decompose anything you want in a zillion building blocks and then pick out only the ones that were useful for that particular image. And those are going to be different than for another image, and so on. So the fact that you have a fast algorithm and then look for a sparse decomposition, the ones that are important for that particular image, was a different mathematical paradigm. And that was actually the first instance of this kind of paradigm in decomposing in building blocks, that in signal analysis that then became, with hindsight, something that was important and that we see in many other applications in what's called compressed sensing. And even in some sense, it's what happens in neural networks. Neural networks have a ton of things that they can do, and depending on what they want to do, they pick the important ones for that application. I've always believed that you can take into account the considerations of the application and still do beautiful mathematics. And so I imposed that. I mean, and I think that's the part of the contribution I feel most proud of, because I think it really needed taking applications, or the potential for applications, as seriously as I did, in order to turn the whole thing on its head, rather than say, I have this beautiful mathematics and this is the algorithm that would come out. I would say, no, I want it to be a beautiful algorithm from the start. Can I get back to the whole underlying mathematics? And it wasn't sure that was going to be possible. I've known other situations where you wanted that, and when you figured it out, well, you just wanted something that wasn't possible. But in this particular case, it was. And I kind of turned it on its head, and it still could work. And that was very wonderful, yes. It was beautiful, and I'm glad that indeed it did penetrate into applications. So wavelets are now part of the basic toolbox for many situations, and many people don't even know that they're using them because it's embedded deeper in toolboxes. So, and that's fine. There is one application where people do realize that they're using wavelets, and I'm always very tickled pink when I see it, or when I'm told. So there are many people who take astronomical photographs who have a telescope and a little motor on it that keeps the telescope moving to follow one portion in the sky for longer, and then can see in the photograph things that they couldn't see with the naked eye. In order to get those photographs, or even photographs that are instantaneous, really sharper, they use software. They use software tools that they download from internet that use wavelets, and typically they know that they're using wavelets, and so they're always very excited when meeting somebody who's worked on wavelets, because they say, "Oh my God, this is what makes my pictures so much." And of course, in these astronomical pictures, you have exactly the situation I was talking about. You have these very star-like objects. You have stars that you want sharp, but you also have nebulas that you want to show nicely. And you have all these other things, the pillars of civilization, of the world, and so on. All these things have smooth parts and very pinpointed things. And you want all of that in its full glory. And it's wonderful that Wavelets help show that glory a bit better.